Okay, today we're going to talk about how to evaluate limits at infinity. And this involves letting x approach infinity. So essentially you're finding the horizontal asymptote, or you're letting x approach a vertical asymptote and the y value would be going up to infinity the closer you get to that vertical asymptote. So that's what we mean when we talk about evaluating limits at infinity. And so in this first example, we want to identify all horizontal asymptotes. Now, a horizontal asymptote is really a simple concept to understand. All it is you're simply asking yourself the question, what is the y value approaching as x approaches a very, very large number in the positive or negative direction? So essentially, you're looking for the limit of the function as x approaches infinity, and you're asking yourself, what does f of x approach? And so that's what we want to look at in this example. So in this particular example, if we let x approach infinity, let's just say for the sake of argument, we plug in 10,000 on the top. On the bottom, we have 10,000 squared plus 1. The plus 1 is going to be negligible compared to 10,000 squared, so we can ignore that. So if you have 10,000 squared and then you square root it, you get 10,000 again. So you can see here that as x approaches infinity, f of x is approaching the number 1. Now if you go the opposite direction, the limit as x approaches negative infinity, you're going to have, let's say, negative 10,000 on the top. And on the bottom, you'll have that same 10,000 because when you take the square root of anything after you square it, it's just going to be that positive number. So this is going to be approaching negative 1. So this is a graph that has two horizontal asymptotes, one at y equals 1 and another at y equals negative 1. And you can see that that is confirmed when you graph it on your calculator. The bigger x gets, the more it flattens out to 1, and the bigger x gets in the negative direction, the more it flattens out to negative 1. Okay, in this second example, we have the function, the limit as x approaches infinity, the function sine of x over x. Now, we've seen this function before, but we have evaluated the limit as x approaches 0. So we have to be careful not to immediately assume that this limit is 1 because we see sine of x over x. We have to look and see what is the limit approaching. Now, this function, if you graph it on your calculator, is going to look something like this. It's going to have a hole here, and let's just actually do it in a different color. It's going to have a hole at 0 because you cannot divide by 0, so you can't plug in 0. But it's going to look like this, and then it's going to flatten out. And then same thing here on this side. It's going to oscillate for a little bit and then flatten out. So as you can see, as we've already noted, as x approaches 0, the y is approaching 1. We've already established that limit in the previous lesson. But as x gets really, really big, the y value is flattening out to 0. And so the question is, why is that happening? Well, as x gets really big, the numerator, sine of x, is always going to be some number between negative 1 and 1. It's going to be trapped between these two very small finite numbers. So if you take a finite number somewhere between negative 1 and 1, no matter what x gets, no matter how big x gets, and you divide it by infinity, let's just say 1,000,000, then you can see that this number is going to be approaching 0 because you have a very small number over a very big number, which is essentially 0. Let's try to apply this to part B. Part B, we could use that same logic, and a lot of these are just simply thinking about the problem. If you plug infinity in, once again, you're going to have 5 times infinity. Well, let's just use 1,000,000. 5,000,000 plus or minus 1, which once again, this is negligible because as you can let x get as big as you want, but the sine of x function is only going to be either 1 or negative 1 or some other number between negative 1 and 1. So it's going to be negligible compared to 5 million. So you have 5 million over 1 million, which is going to be 5. So this limit is going to be 5. Or you could do it and break it up into 2. So we'll have 5x over x plus sine of x over x. And the limit as x approaches infinity of both of these. So this is just going to be the limit as x approaches infinity of 5, because the x's cancel, plus the limit as x approaches infinity of sine of x over x. We've already established that this limit is 0 because of the last problem, and the limit as x approaches any number of a constant is just that constant. So 5 plus 0 is going to be 5. All right, let's switch gears and talk about how to find a vertical asymptote. We've done this in pre-cal before. So a vertical asymptote is simply, you're asking yourself the question, what number would, or numbers would cause you to be dividing by 0? You cannot divide by 0 in math. So you essentially have to say, what number or numbers would cause me to divide by 0 or to make the denominator 0? In this first example, it's pretty obvious. X cannot be 0. So the vertical asymptote would be x equals 0. So if you had a graph and you were graphing this, you would put a vertical line, dotted line at x equals 0 to remind yourself that x can never be that number. So this particular graph actually looks like this. We know that because the function, the exponent is even, so it's going to have even symmetry. All right, part B, we're going to change tangent of x into sine of x over cosine of x. And so now we have to ask the question, what angles would cause the cosine of x to be 0, which would cause us to be dividing by 0? So we would say, okay, let's just think about our unit circle. Our unit circle has coordinates 1, 0 here, 0, 1 there, negative 1, 0 there, and 0, negative 1 there. And you can see that the cosine is going to be 0 at pi over 2 and 3 pi over 2. So pi over 2, 3 pi over 2. But those are not the only two angles, because pi over 2 is here, and then 3 pi over 2, then 5 pi over 2, then 7 pi over 2, then 9 pi over 2. So all odd multiples of pi over 2. So how do we express that? Well, we could write 2n plus 1 times pi over 2. Let's see if that works. So we'll say x equals, that's our vertical asymptote. When n is 0, this 2n goes away and you're left with 1 times pi over 2. Check, that's our first one. When n is 1, you have 2 plus 1, which is 3 pi over 2. And when n is 2, you have 2 times 2, which is 4 plus 1, 5 pi over 2, so on and so forth. So that would be a good, fancy way of expressing all odd multiples of pi over 2. All right, we are going to skip example 5 and 6 this year because they are really not covered on the AP exam, although they are in your notes. So we're going to skip right to the last example, example 7. Determine the following limits. We're going to let the limit as x approaches 1 from the negative side. You have to pay attention to that. And x squared plus 1 over cotangent of pi x. First thing I'm going to do is I'm going to rewrite this, and I'm going to write it as the limit as x approaches 1 from the left of x squared plus 1 times tangent of pi x. So we know that we can bring the cotangent up to the top and it becomes tangent. And then I'm going to rewrite this again as x squared plus 1 times tangent, which is sine of pi x over cosine of pi x. That way, when I plug in my limit, I can really see what's going on here. So I'm going to plug in 1. 1 squared is 1 plus 1 is 2. So I have 2. And I'm going to plug in 1 into this x. and that gives me sine of 1 pi. Pi is 180. It's on the left-hand side of unit circle. The y value is 0, so essentially 0. And on the bottom, if I plug in 1 here, I'm going to get cosine of 180, which is negative 1. So you have 2 times 0, which is 0, divided by negative 1, and that's just going to give me 0 as a limit. All right, part B is a very similar problem. I'm going to rewrite this as the limit as x approaches 0 from the positive side, and I'm going to write 3 cosine of x over sine of x. So now we have to really pay attention once again to which direction it's coming from. So I'm going to plug in 0. Actually, what I'm going to do is I'm going to draw both the cosine graph and the sine graph. Let's go ahead and do that. Show you a different way of getting this answer. So our sine graph is going to look like this. And we'll do the other side as well. And our cosine graph is going to look like this. And similar on the other side. So why don't we label these as sine of x and cosine of x. So why don't we analyze as x gets closer to 0 from the positive side of the cosine graph. So from the positive side closer to 0, the y value is approaching 1. So on the top we have an answer of 3 times 1. And on the bottom, x approaches 0 from the positive side of the sine of x. So now we're coming from this direction, and we're approaching x equals 0, and we see the y value is approaching 0, but it is approaching 0, it's going to be slightly positive. So maybe I'll write something like 0.00000001, but it's going to be a positive number. So what do we have? We have 3 divided by a very, 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 very small number, but positive. That's going to be approaching, it's going to be approaching infinity. Now you have to pay attention to which direction, because if I change this to a negative, watch what happens. The limit as x approaches 0 from the opposite side, the negative side. Well, from the cosine graph, it's still approaching 1. So the top is still going to be 3 times 1. But on the sine graph, if I'm approaching x equals 0 from the left side, it's going to be a number, the y value is going to be very close to 0, but it's going to be slightly negative. So that's going to be a negative 0.000001, which is going to be a positive over negative, which is going to be approaching negative infinity. So just pay attention to which direction that you are evaluating the limit from.